Okay, let's move on. We continued to talk about periodic mesoporous materials in the last class, and we learned about a different approach to make them, which we called nanocasting, which is also called hard templating. In this approach, you start out with a periodic mesoporous material, and then you fill the pores of that mesoporous material with a precursor of the target material, and then you produce the target material inside of the pores of the hard template. In the last step, you remove the hard template to produce then the periodic mesoporous target material. So this process is usually done at ambient pressure, but it can also be done at high pressure. And this is a route to produce mesostructures of high pressure phases. Okay, one can also produce mesoporous high pressure phases. So this is so mesoporous high pressure phases are unusually in the sense that high pressure favors dense phases over porous phases. And that technique of nanocasting at high pressure can overcome this principle. One can actually use high pressure in order to produce a porous phase, in particular, a porous high pressure phase. So here is exactly how the nanocasting at high pressure process works. So you start out with a periodic mesostructured composite. Okay, so for example, you can start out with a periodic mesoporous silica material, and you can fill that periodic mesoporous silica material with carbon. Okay, that produces a periodic mesostructured silica carbon composite. And then you can apply high pressure in order to convert either one of the one phases or even two phases. Okay, because this mesostructured composite here is not porous anymore, the pores are being filled, and therefore there is no thermodynamic driving force for transformation in a denser structure. Okay, so you can either transform the hard template phase, okay, into a high pressure phase. Okay, so for example, the silica phase, and then remove the carbon again after the high pressure synthesis by combustion. Okay, and this way, high pressure phases of silicon dioxide have been produced. So coesite, which forms above 4 gigapascals, and stisovite, which forms above approximately 12 gigapascals. When you stay below 4 gigapascals, then you can also produce periodic mesoporous quartz. So quartz is not a high pressure phase, but the crystalline phase. And typically, periodic mesoporous silicas are having amorphous pore walls. And it's actually not possible to crystallize these pore walls at ambient conditions. If you choose high pressure conditions, you can do this, because high pressure greatly facilitates crystallization, and that is basically for two reasons. So first of all, there's a kinetic reason. You can activate bonds using pressure. So when you apply pressure to a material, then you apply mechanical stress to the bonds, so the bonds break more easily and also reform more easily. So this way you can actually overcome activation barriers of reconstructive bond formation. And secondly, there is a thermodynamic reason for this. So amorphous phases tend to be less dense than crystalline phases. So by applying pressure, you actually set additional thermodynamic driving force for the transformation of the amorphous phase into a crystalline phase. So using nano casting at high pressure, you can also produce periodic mesoporous materials with crystalline pore walls that are not accessible at ambient pressure. Okay, so in principle, you can also then convert the second phase inside of the mesopores into a high pressure phase. In the case of carbon, that would be diamond, and then oxidize the, and then after the high pressure synthesis, back at ambient pressure, dissolve the silica phase, for instance, by HF to make mesoporous diamond. But this has not actually been demonstrated yet. It's actually significantly more difficult to do because, as it turns out, the preservation of the mesostructure requires that at least one of the two phases remains chemically inert under the reaction conditions. When you activate them both, then there's a driving force for the mesostructure to disintegrate, okay, because the mesostructure itself is only metastable. Therefore, this step here is thus far a hypothetical step. It has not been experimentally accomplished thus far. All right, so another potential extension of this chemistry is to produce one-dimensional nanostructures of high pressure. So when you have meso channels which are not interconnected, okay, which are one-dimensional, then the transformation of the phase inside of the mesochannel into a high pressure phase produces one-dimensional nano rods of that high pressure phase. And these are spatially separated from each other, so that after the template removal, you get individual nanorods, despite the fact that you have applied high pressure. In the synthesis, you can actually avoid the aggregation of one-dimensional nanostructures this way, and that makes nanostructures of this type then processable after the synthesis. Okay. So how do you produce high pressure? So there are multiple different techniques available for that, and which one you choose depends on which pressure and temperature range you want to achieve, but it also depends on how much of material you actually want to make. Okay, so that is generally an issue in high pressure synthesis, because pressure is defined as force over area. Okay, so that means if you want to apply high pressure, then if you want to keep the area large, okay, meaning that you want to make more material, you have to go to very high forces. Okay, you have to produce very high forces. Okay, if you do not want to produce very high forces, or you cannot produce very high forces, then you just keep the area very small. Okay, but that has the disadvantage then that you can produce only a very small amount of material. Okay, so one technique that can go to fairly high pressures, actually 27 gigapascal, and can also provide simultaneously very high temperatures of about 3000 degrees Celsius, is the so-called multi-anvil technique. And this technique also produces still relatively large sample sizes in standard laboratory experiments. However, by large, we mean here amounts in the order of a few milligrams, maybe tens of milligrams if you keep at pressures below 10 gigapascals. Okay, so here is how the technique works. So the key of the technique is that you apply the pressure isotropically to the sample, but still use uniaxial pressure from a hydraulic press. So you place your sample inside of a magnesium oxide octahedron, okay, which is physically shown here. And the schematics of the inside of this octahedron is actually shown here. So this is a cross section through that octahedron, okay? So the actual sample is here. So this is shown in purple here. And your sample is inside of a capsule, okay? The capsule material can be varied. So platinum capsules are popular because platinum is a quite chemically inert material, but it can also stand very high temperatures. So you actually fill your sample into platinum capsule and you weld that platinum capsule shut, okay? And then that platinum capsule is surrounded by a sleeve of an electrically conducting material. The electric conducting material depends on the pressure range that you want to use. So below approximately 10 gigapascal, you can use graphite, and the graphite tube will then act as a resistance heater, okay? Above 10 gigapascals, you cannot use graphite anymore because the graphite will start to convert into diamond, the high pressure phase of graphite. In this case, you can use other materials, for example, lanthanum chromate. Okay, so now this graphite or lanthanum chromate sleeve is then surrounded by a zirconia sleeve typically. Okay, this is shown here in light yellow. And this zirconia sleeve acts as a thermal insulator, okay? So it minimizes the amount of heat which is being transferred from the graphite resistance heater here, okay, to the outside. So it confines the heat to the, well, to the inside of the octahedron, okay? So then you see further here, there are some alumina end caps. So these are just to fill the space. And above these alumina caps, there are molybdenum plates. Okay, and these molybdenum plates are in contact with the graphite resistance heater. Okay. And they allowed for the flow of electrical current from the tungsten carbide cubes that surround that octahedron. I will talk about that in more detail shortly, and the resistance heater itself. Okay. So this octahedron, as it is shown here, will then be placed in between 8 truncated tungsten carbide octahedra that you actually see schematically here. Okay, you see here again 4 of the 8 tungsten carbide octahedra. So these tungsten carbide tungsten carbide cubes, not octahedra, they act as anvils that transfer the pressure from or transfer the force from the hydraulic press to the octahedra. Okay, So these are truncated. You see a truncation here, and the same truncation here would be on the other corner. So that that triangular face of the octahedron, magnesium oxide octahedron, would fit precisely on the tungsten carbide cube. Okay, you see further that around these truncations there are gaskets, and these gaskets are made from pyrophyllite. We have discussed pyrophyllite previously. So pyrophyllite is a layered silicate, okay, which has a very high temperature stability. So due to the layered structure, it actually acts as lubricant, preventing that the tungsten carbide cubes touch each other during the high pressure experiment. At the same time, they are very temperature stable. All right, so further you see that there are thermocouples here, and these thermocouples, they lead inside of the magnesium oxide octahedron, and they serve as points of temperature measurement, okay? So this is actually not shown in the schematic here. So in addition to that schematic here, we should consider that we have thermocouple leads, okay, that actually lead here to the well, top of the platinum capsule, okay, and these thermocouples touch approximately here at this point. All right, so now you see here a completely assembled cube. So this cube is now containing the magnesium oxide octahedron in the very inside, okay? You see the 8 truncated tungsten carbide cubes placed around it, and these tungsten carbide cubes are being held together by glass fiber plates, okay? Now you see here, these leads here, so these are the 2 thermocouple leads that actually lead to the inside of the octahedron, okay? So now you see also here, see copper connects here. So this is how the electrical current will flow, okay? It will flow through this copper sheet to the cube here, to this cube, tungsten carbide cube, through the furnace inside of the octahedron to the opposite tungsten carbide cube, okay? And on the other face, on the opposite face of this face, you would then have here another copper sheet. Okay, so the tungsten carbide itself, I should say, is electrically conducting. It's because it's a metallic face. Okay, the tungsten carbide is also a very hard material. This is another reason why you choose tungsten carbide. It's actually the hardest metallically conducting material known. All right, so now you have assembled your cube here. So in the next step, you place your cube in between 3 wedges, okay, that have provide a placeholder for the cube, okay. So you place your cube with the body diagonal standing perpendicular to the horizontal surface into these, in between these 3 wedges. Okay, and these 3 wedges are made from hard steel. Okay, in the next step, you place actually 3 other wedges on top. Okay, and that cylindrically assembly, okay, is then being placed into a so-called Walker module. Okay, so this is nothing else but well, a cylindrical piece which has a cylindrical cavity into which this assembly here with the overall 6 wedges fits. Okay, So now basically you can close this Walker module here with a lid. All right. And then you can place this part here underneath a hydraulic press, okay, that is able to apply force uniaxially via via pistons and a cylinder. Okay, and as you apply the force, where the uniaxial force gets translated from these two faces here, okay, of the Walker module to the 6 faces of that big cube here, okay, and from there to the 8 faces of the octahedron, and from there to the sample, okay, whereby current is flowing from the top plate here through the tungsten carbide cubes, through the sample to the opposite tungsten carbide cube, and from there to the bottom plate. Okay, therefore the top and the bottom plate here, they must also be electrically insulated from each other, and that you arrange actually by placing here a thin plastic sheet as a liner. Okay, so you can ramp up the pressure slowly, typically at a rate of 1 gigapascal per hour, and then you can start heating the sample, and you can achieve temperatures of up to 3000 degrees Celsius. Okay, and after the high pressure synthesis is done, okay, you simply remove the force, you disassemble your Walker module, okay, then you take a hammer, right, and hammer on the octahedron. The octahedron falls apart, and you still have your sample in your a platinum capsule. Okay, and then you just actually take sandpaper, okay, and then you open the capsule by sandpapering it, just mechanically removing the platinum until you actually see your sample, and then you can extract your sample from the platinum capsule. Okay, so this is how a high pressure synthesis with a multi-assembly works, and that method provides you enough sample for a post synthesis investigation. Okay, so you still have enough to, for instance, characterize your material by X-ray diffraction. You can do electron microscopy on it, and you can characterize it with other techniques. Okay, but with this technique, you are limited to about 27 gigapascals. There are ways to further improve the pressure range, but they are not done routinely. Okay, so for example, you can also we can replace the tungsten carbide cubes by sintered diamond anvils. Okay, but that's not routinely done because these kind of anvil materials are very expensive. Even the tungsten carbide is actually pretty expensive, and these anvils don't last forever. Okay, so you can maybe use them for a dozen of times, then you will actually start to see cracks in them, so are actually a consumable material. All right, so now the other major high pressure technique that I wanted to discuss here is the diamond anvil cell. So the diamond anvil cell allows you to go to significantly higher pressures, up to 707 gigapascal. That's the highest claimed pressure that has been achieved thus far. But the sample sizes become very small. On the other hand, you can actually produce the force necessary to go to these extremely high pressure practically by hand. And such a diamond anvil cell is a very small size. You see actually one here, so you can easily place it on the table. And then you see actually you have here these set screws, and you can actually just turn these set screws mechanically by hand, yeah, in order to apply the pressure to the diamond anvils that are inside of here. Okay, so by hand force, you can actually produce pressures which are higher than the pressures at the core of the Earth. So at the core of the Earth, we have approximately a pressure of 300 gigapascal, so 770 gigapascal. This is about twice as much. But as I said, this comes at the expense of sample volume. So your sample volume is only approximately 10 to the minus 7 cubic centimeters. Okay, so it's very hard to actually do post-analysis of your sample. On the other hand, you don't need to in many cases because of the transparency of the diamond anvils. Okay, so within such a diamond anvil cell, as you see it here from the outside, you actually have two diamonds, okay, that act as anvils. And these two diamonds have certain culet sizes, which are in the order of up to a few millimeters. Okay. Now, in this case, enlargement here, it would be 1.8 millimeters, but that actually varies. So these surfaces are not always flat, so they actually have a bevel angle, which is in this case 2 degrees. So that's actually this angle here. And you choose these bevels in order to minimize the forces that act on the corners here, okay, which can actually make your diamond break. So actually you enhance the lifetime and the pressure range that you can reach for your diamonds. Okay. So these two diamond anvils, they do not directly touch each other. Rather than that, you actually have a gasket, which is a metal gasket. For instance, rhenium is a popular material that holds the sample. Okay, so your metal gasket is actually just a cylindrical metal piece. You actually see here an actual photograph of it. Okay, in between your two diamonds. Okay, with a small hole in it. Okay, which is typically a fraction of a millimeter. Okay, can be between approximately 0.1 and 0.5 millimeters wide. Okay, and in that hole there is your sample. Okay, and you see from that your sample amount will naturally be extremely small. Okay, but with this technique you can apply an extremely high pressure by hand force, and at the same time you can investigate what actually happens to your sample by spectroscopic techniques, because your diamond is transparent. Okay, so you can, for instance, do Raman spectroscopy through your diamond anvils. Okay, or you can do X-ray diffraction through your diamond anvils. You can do IR spectroscopy through your diamond anvils because of the transparency of your diamond. Okay, because of the transparency of your diamond, you can also calibrate or measure the pressure via ruby fluorescence. So typically you place a little ruby crystal together with your sample into that very small space. Okay, and measure the pressure inside of your diamond using ruby fluorescence, which is pressure dependent. Okay, so as you increase your pressure just by turning your set screws, okay, the ruby will experience a higher pressure, and its fluorescence will actually shift in wavelength. Okay, so you excite actually a ruby with a laser, okay, that you actually shine through your diamond anvils, okay, and you excite well, the ruby that you have together with your sample, and then your ruby fluoresces. Okay, and the exact wavelength of your fluorescence depend on the pressure. Okay, so this is how you know what pressure you have in your diamond anvil cell. Okay, you can also heat a diamond anvil cell. Okay, and there are various methods to do that. So for relatively low temperatures, you can actually just place the entire diamond anvil cell into a furnace. So that works for temperatures up to about 1000 degrees Celsius. The disadvantage of that is that the pressure in the diamond anvil cell can actually change significantly due to thermal expansion issues of your material. The alternative is actually laser heating. With laser heating, you can go to temperatures larger than 1000 degrees Celsius. You can go to extremely high temperatures up to several thousand degree Celsius. And in this case, you actually use an IR laser that you shine through your diamond, and then your IR laser heats the sample through selectively interacting with the sample. So this way you really only heat the sample, but not your diamond anvil cell around it. The disadvantage of this technique is, though, that the temperature inside of your diamond anvil cell or throughout your sample may not be very uniform. So there can actually be a pretty large temperature gradient occurring. Another important experimental parameter is the pressure medium. Okay, so you can actually use, for instance, solid noble gases like argon as pressure medium, because otherwise, because of the uniaxial pressure that you apply to your diamond anvil cell, you may have actually a pretty large pressure gradient, okay, from the inside of your sample to the outside of your sample. So if you embed your sample in a hydrostatic pressure medium, such as solid argon, you can minimize these pressure gradients, and you have a homogeneous pressure within your sample. Okay, so these are the probably two most common techniques in order to do solid state synthesis at high pressure. Of course, there are other high pressure techniques. One of them I actually talked about previously already. That's the solvothermal method in autoclaves. We have discussed the hydrothermal growth of quartz crystals in hydrothermal autoclaves. There are also monothermal autoclaves. There are also other cells that are suitable for high pressure synthesis, for instance, the Paris-Attenborough press. But I'm not discussing all of the techniques here for time constraints and clarity reasons. All right, then we are finished with this. And unless there are questions about this, we can move over to the next sub-chapter in our chapter about porous materials, which are macroporous materials. So are there any questions at this point?
I have just like a curious question. So when you use the laser heating for the diamond anvil, do you have to worry about the possibility of photothermal expansion on your sample causing a pressure gradient as well? Or do you think that the high pressure environment in general prohibits the photothermal expansion of the sample?
Yeah, that is a good question. So photothermal expansion, I believe, can be an issue. However, it typically doesn't change the pressure much, just because the external pressure that you apply to the sample is typically extremely large.
Right, right.
Basically, the additional pressure through photothermal expansion that you are creating is, to my knowledge, not significant relative to the outside pressure.
Right.
But in principle, yeah, that's also a factor. That's
cool. Thank you.
Consider.
Thank you. Cool. That's it.
Any other questions? All right, then we can actually move from the mesoporous materials to the macroporous materials. And now we are talking about, materials that have pore diameters larger than 50 nanometers. So macroporous materials are materials with pore diameters between 50 and 1000 nanometers, typically. Okay, now the concept of nanocasting, which we discussed previously, can now also be extended to form macroporous materials. We only need a different template. And a popular template that you can use is latex or silica spheres that are packed in periodic arrays. Okay, so these latex or silica spheres have typically diameters in the order of, well, tens to hundreds of nanometers. Okay, and for that reason, the space in between, well, these spheres is also in the macroporous range. Okay, remember that we cannot pack actually spheres closer than with a 74% packing density. Okay, and you have well, again, tetrahedral holes and octahedral holes, which are actually not that much smaller than the sphere sizes themselves. Okay, so in a range of latex or silica spheres in the order of tens to hundreds of nanometers is a macroporous material itself. Okay, but using nanocasting, you can increase the porosity by inverting the structure. Okay, so what you can do is you infiltrate a close packed structure of these spheres with a suitable precursor of your target material and fill actually the voids in between the spheres, which is at least 26% of the space. Okay, and then you remove the spheres with a suitable method. Okay, and that leaves you then the inverted structure behind, which is also a macroporous solid, but a macroporous solid with significant higher porosity than the original structure. Ideally, you would have a porosity of approximately 74%. Okay, because now the volume which was previously occupied by the spheres is now empty space. Okay, for this process to work, of course, you have to have a template which is movable. So latex is good because you can just combust it. Silica is good because you can just dissolve it in HF or in a base. Okay, so of course everything must be compatible with the process conditions. Of course, your precursor must be able to wet the particles in order to fill out the space in between. So capillary reactions must be positive. And the latex in the silica spheres must have or should have a narrow pore size distribution, because otherwise you're not producing an ordered material. You produce a disordered material, still that disordered material would be macroporous, but if you strive for order, you would really want to use spheres that are uniform in size. Okay, so how do you produce actually such silica or latex spheres? So silica spheres you can produce by a process which is called the Stöber process, developed by Stöber in the 1960s. So this process, even though very old, is still mechanistically not well understood, but it works very well in order to produce very uniform silica spheres with sizes that can be tuned between 50 nanometers and approximately 2 micrometers. Okay, and what you do is you actually dissolve a silica precursor such as tetraethoxysilane in a mixture of ethanol and water that contains ammonium hydroxide. Okay, and then under these slightly basic conditions, the condensation of the silica particles, this nucleation of silica spheres is started, but the silica spheres are somewhat charged. Okay, so they have negative charges on the surfaces due to the presence of terminal oxygens, which are then charge compensated by ammonium ions. Okay, so that actually prevents these nucleated silica spheres from aggregating together. Okay, so rather than that, further monomer would actually assemble around these spheres and make these spheres grow, but keep them apart from each other. Okay, leading then to silica spheres of almost monodisperse size. So this is called the Stöber process. So how do you make latex spheres? You see this schematically over here. So in order to produce latex, you basically polymerize styrene in the presence of a divinylbenzene linker that actually interlinks the styrene, cross-links the styrene to make a three-dimensional polymer in the presence of a surfactant and a radical initiator, for example, AIBN. You see here the structure of AIBN. So AIBN stands for azo bis isobutyronitrile. Okay, and that molecule can disintegrate into nitrogen molecules in these dimethyl cyano radicals. Here, and these radicals can then react with styrene and divinylbenzene in order to polymerize the styrene. So how do you get that polymer in form of a monodisperse spheres? You do a so-called emulsion polymerization in the presence of a surfactant. Okay, and these surfactants in an aqueous solution, they form spherical micelles. Okay, at the same time you have your monomer droplets. Okay, and you stir your entire solution. Okay, so now what happens is that the micelles swell and become larger in size at the expense of the monomer droplets, okay, that may also have surfactant molecules in the periphery, okay, until the monomer droplet, these monomer droplets, which are larger in size, are completely consumed, okay. So at the same time, you have your initiator in the solution, and the initiator preferentially starts the polymerization inside of the micelles and not in the monomer droplets, okay? And that is because the monomer droplets are significantly larger, so the surface to volume area is significantly smaller. And therefore, just for statistical reasons, such a radical initiator is much more likely to enter the micellar structure and initiate the polymerization. Initiate the polymerization there. The polymerization occurs until basically all monomers being consumed, leading then to nearly monodispersed latex particles. Okay. So now your next task is to arrange these particles into colloidal crystals with high periodicity. And the most simple way is actually to use gravity to do this. So disperse your particles in a solvent like water, and then you just let the water evaporate, okay? And the water will slowly evaporate, and gravity will, over the time, let the particles sink to the ground, and basically thermal motion will arrange them in an ordered closed packed lattice. Okay, so this is a very simple method how you can actually produce a colloidal crystal with a high periodicity. So another way is to use what is called convective assembly. So this is a good way to make colloidal crystals with high periodicity as a film on a substrate. So you actually place your colloidal solution on a heat source, and then you have a temperature gradient throughout your solution. So at the bottom, where the solution is closer to a heat source, it will be somewhat hotter than further away. So that will actually produce convection, okay? And then you have a substrate here, okay, which has a meniscus with the surface of the liquid. And then capillary forces during drying cause an assembly of these colloidal crystals in the meniscus. And then as you evaporate the solvent over the time, you're forming a colloidal crystal on the substrate. So this way, you can actually produce extremely flat but large area colloidal crystals, which are also called opals of controllable thickness. Okay, so I see our time is over. So let us stop at this point.